All right, I think we should start. Now is the time. Okay, so last time we looked at a permutation group, and one of the sort of interesting results which we discussed was the number of the assignments which are needed to do a permutation in place. And if you remember, the formula which we sort of obtained was that in order to do a permutation of n elements, the number of assignments is equal to n, total number of elements, minus number of trivial cycles, elements which are not moving far, which actually remain in place, and plus the number of cycles. Okay, so now we're going to actually implement a whole bunch of these permutations because they happen to be extremely useful in practical programming tasks. So believe it or not, today's lecture is of immediate practical importance. We're going to have code written which I use all the time. Doesn't mean you will use, but the reason I use it all the time, sort of metaphysical reason, comes from the following thing. There are two things which one could learn from mathematics. One thing is that you could abstract. You could go from things like numbers to things like rings. And these properties of rings subsume the properties of numbers. So you could write code which will not just work on integers, but will also work on polynomials. Remember that? But there is another point, and in some sense, the point of even greater significance. You see, what we learn from mathematics, especially when we read good mathematics written by great mathematicians, is their ability to decompose the discourse, whatever they're describing, in a sequence of small lemmas. You seldom have something which goes on for pages and pages and pages. You say, and what should we learn from that? What we should learn from that we should not have code which goes for pages and pages and pages, because it's most likely wrong. It is my ability to figure out whether code is correct stops at about 10 lines. If you have a procedure with more than 10 lines, most likely I can never figure out what it does. You say, well, you are stupid. That might be, but other people who read your code might be as stupid as I am. That is, it's a very important thing to strive to this decomposition of things into small, independent lemmas. What do I mean by independence? Again, a good example of some independent procedure would be a procedure which takes a sequence of totally ordered elements and finds its minimum. Could be done, yes? A similar procedure, which is not independent, is something which goes through particular data structure, finding the object of the smallest price. Right? Sort of instead of looking for a minimum, you start saying that it's like, there are tribes which have multiple words for integers, depending whether it's polar bears or fish or igloos. Right? Sort of the great progress which mathematics sort of allowed us to have is there's one word for one. We don't need to. And the same thing with our code. I mean, we have to make it as independent of the immediate application as possible. Right? There is this profound, profound thing there. And we will start looking at some very particular piece of code. I heard the term software patterns. There is a book. I don't know what these people are talking about. But this is as close as I know about software pattern. Something like while condition, swap some pointer with some other pointer. So what does it do? It somehow permutes, moves these things and these things like so. Right? It's a simple fragment of code. It's not a procedure, because we don't even know what the condition is, which somehow a good building block for a permutation. We're going to build permutations. So let us see how we could finish, so that we come with this intuition saying, whole bunch of different codes, I seen that. So you see sort of what could I extract out of it? You start from this fragment, and then you try to make it into a procedure. Everybody, by the way, understands how? I mean, it's while some condition holds, keep swapping and moving. Okay. So it swaps ranges. There is a very, very important notion of a range. In any sequence, you could have a range, and there are 4 kinds of ranges. Ranges could be semi-open or closed, meaning they include the last element or they're just bounded by the last element. Mathematicians knew about that for quite a while, and we should know too. So bounded, semi-open or closed. Or bounded, that is, a range is defined by 2 iterators. We will learn in the 4th journey in full generality what iterators are, but right now think about pointers, 2 fingers pointing into some data structure. So they could be bounded, you say, from here to there, fingers. Or it could be counted, from here, 5 elements. Observe that there are some strange things. For example, the guy in this corner, which is counted closed range, of course, requires that n is greater than 0. You cannot have closed interval, which is also empty. Right? It just doesn't happen. Right? So, but sort of these are 4 things. So we will try to apply this somehow to these ranges. And a first very simple procedure is the procedure that takes one range, bounded semi-open range, explicitly from F0 to L0, from here to there, not including. And it takes the second range implicitly. Basically say, the second range is starting from here, and who knows where it ends, but it's long enough. Right? That is, we do not care about how long it is, because we know it's somehow long enough. And what we then could do, we could keep swapping while we don't move first to become equal to last. Just go and swap and swap and swap and swap. Right? So it's literally just this. Right? Now, several design questions. Why do I return F1? Because I don't know about the other range. Right? And I don't need to do any extra work to return it. Right? It's a useful thing, and it's free. So which comes to one of the fundamental laws of designing useful interfaces. A procedure should return all the potentially useful information it's computed. I don't mean try to compute information which you don't need to compute. Because, I've seen code, even in some local code bases, where people say, oh, just in case I will do the count, or just in case I'll do something. No, it's not what I'm asking. Don't do extra unnecessary work. But if you've done something, consider returning if it's useful. Okay? Again, how do we know that things are useful? This is, again, tricky. We know only when we analyze all the potential uses. It's a two-pass thing. I wish I could tell you how to distinguish useful from useless. Lots of experience helps. Right? And eventually you start recognizing sort of, well, this is not, I'll give you some examples right here. And the second thing, the law of separating types. That is, a naive person, like when I was young, I would encounter something like that. I say, I'm just doing permutation. Therefore, the type of this range is the same type as the other range. I don't need to know that. It does make things faster. It doesn't change the code. It just throws generality away for no reason. So I, instead of doing this, just using the same type for both ranges, I could disjoin them. There is no penalty. Right? And it suddenly becomes much more powerful thing. I could, for example, swap things in a linked list with things in an array, and it just works. Right? There is no penalty. So the law of separating types. Now, this is one of potential interfaces. Again, I could swap ranges when both ranges are given explicitly. Observe that they're not the same size. So I have to carefully assure this is what is done in while statement. Sort of the first condition says the first range is not empty, and the second range is not empty. Then keep swapping and reducing the ranges. All right? So it will stop when we will exhaust the smaller range. Right? Very simple. Now, what do we have to return? Again, now, as before, we had to return one guy. We could have returned both, by the way. We could have returned a pair. But it is, again, it's useless. Why is it useless? Why F0 is useless? Because the guy who called us knows what F0 is going to be. Is going to be equal to L0, which he knows since he gave it to us. That is, do not tell me what I already know. It's, again, one of these things, sort of think about not overwhelming people with useless information. So, but here we clearly need to return a pair. Right?
You kind of know this also, which is minimum of L0 and L1.
Yes, but I don't know which. Right? So the shortest way of, yes, I could introduce Boolean flag, and but this is the shortest way of actually returning the information. Because I am the caller, I could find out which range is exhausted by comparing, say, the first element of the pair with L0. That will tell me which range is exhausted. Only one comparison, one Boolean. Right? It's not, well, yes, yes. So we will see. We will see. Observe that we sort of not going to check this case here. For example, if first one is exhausted, I'm going to return without checking if the second one is exhausted. You could ask me, why don't you? Well, because I don't want to do unnecessary computations, which will take you exactly as much effort to do as it will take me. Right? It's not throwing away useful information is the rule, not doing everything you can. So the law of completeness, when designing an interface, consider related procedures. Again, there is a school of thought among some programmers who think that you have to have one interface which does everything. For example, we have data structures, or let me put it like that. I've seen data structures which have in the method called insert or erase. And you could actually have a data structure with one method: insert or erase or find length or do whatever. And then you play, and we have them. Sort of, you shouldn't be doing that. That doesn't mean completeness. Completeness means it's not putting everything into one interface, but considering related interfaces and sort of designing, investigating, exploring the space. This is, as we looked at these two routines, and both of them are needed, sort of, not just one. And then there is a third one. Sometimes, we'll see these cases very shortly, you actually know the length. It's not bounded as a counted range. So what you do, you turn it into a really nice procedure. Why it's nice? Why it is better? Because it has an explicit trip count. The compiler could easily figure out how many times we will iterate through this loop. How many times? N times. Right? Therefore, it's easy to do all kinds of transformations. For example, it's easy. I forgot. It's not here. But it's easy to write. My memory is giving up. What I wanted to say, it's easy to have a problem, and I thought the problem is right here, to write an unrolled version of that. But apparently the problem will be later with a different piece of similar code. So again, and we again return the pair. Because we move by n both points, we better return them. Now, the interesting question, why don't I provide this? Yes, thank you. That's still your homework, but you use this, you sort of explore this logic. I'm not supposed to do everything for you, right? If you could do something by just calling min, that's good enough. I don't need to provide a special interface. Now, let us go back to permutations. We're just ready to handle a whole bunch of stuff about them. There is one great thing which we discovered, which mathematicians never found out. It's better to index from 0, guys. It's really better. People say, oh, it's a hack because how address arithmetic works. Maybe that's how it was discovered. But now, after having doing mathematics in these both terms, let me assure you, indexing from 0 is a more natural thing. For example, if we want to define a permutation which rotates n elements to the right by k, oh, it's so much more convenient if my indexes go from 0, because the transform becomes I plus k mod n. I could write it with 1, but it's oh so very ugly. It's actually what happened while during preparation of these slides. Was it you who was? Or it was either you or Neil. It was Neil. Okay. So we tried doing it mathematical way, and when we observed that the index transformation was mathematically so ugly that I decided that I'll switch permutations to start from 0 and put this slide in, explaining that it's a better mathematics. So remember, when we were writing permutations, we were writing 1 goes into this. Now we're writing 0 goes into this, 1 goes into this. Indexing is from 0. A rotation, and that's what we're going to be sort of one of the central things for this lecture and a very fit thing to end this journey. Because as we will observe, rotation, a very, very useful primitive in programming, it's intimately related to GCD. Okay, so what is a permutation of an element, rotation of n elements by k? It's you take every element and send him to k mod n. Right? So if you rotate around, circular rotation. And it is an amazingly important algorithmic primitive, of which you, of course, do not know, because it somehow escapes people's attention. And some of you might know how to do rotations, but most people never encounter it. It's, for example, it implicitly appears in solution to one exercise by Knuth, but it's not named, so you cannot even extract it from Knuth. And what I claim, it's like a screwdriver. It's one of the fundamental tools. Why it's one of the fundamental tools? Because it's very often what you want to do is you have some kind of a buffer. You want to remove a middle part of this buffer. For example, you implement it in an editor. What do? You rotate it out. Sort of the things at the end is your kill buffer. The text is the beginning. And you move things from the text to the kill buffer by doing rotate. Okay? It's extremely important to implementing all kinds of fundamental data structures. And as we shall see, especially during the next journey, the third journey, it appears in all kinds of algorithms. If you want to sort well, you better know how to rotate well. So why is it not known? Don't ask me. Again, I have been trying for decades to tell people about this wonderful thing, but nobody listens. It isn't the standards. It's part of STL, but again, people don't know what. I mean, people say, well, we only use vector. And let us see how we will. And here I have to tell you that I'm going to cheat a little bit. Because how do I know what's the right interface for rotate? Well, I know what's the right interface for rotate because I wrote many algorithms which use it. So I couldn't really show it from the first principle. I could make it plausible. But you will truly see why the interface is good only when we're done with the third journey, because you will see that it just pops out in every piece of code. That's the interface you need. Not some other interface, but interface just like that. So design is a multi-pass activity. In general, programming is a multi-pass activity. One thing I observed, not at A9, I found it out at Adobe, that a modern programmer thinks that it's sort of an honorable thing, never look back. You sort of start writing code, and you have to finish it without ever looking back. It's not fair to look back. It has to be a one-pass activity. Guys, no. You cannot do anything unless you write it and rewrite it and rewrite it and rewrite it. The same goes for interfaces. So experience shows that the convenient interface is not viewing rotation as nk, but viewing as a 3-iterator, first, middle, last, and viewing rotation not as, if you like, rotation, but as an exchange of unequal blocks. We rotate 8 guys like so, right? Obviously, it's the same thing. It is just a circular rotation, but it also an exchange of unequal blocks. And that's where the algorithmic difficulty, of course, is, because it's very simple to exchange equal blocks. We actually wrote swap ranges which will do just that. But when we want to exchange in place 3 with 5, they don't quite fit because 3 is actually smaller than 5. Right? So this is useful interfaces, 3 pointers. Now, let's just show an example of rotate. First, middle, last. First points to 0, middle points to 2, and observe our ranges are semi-open. So the first range, range FM, is actually 0, 1. The range ML is 2, 3, 4, 5, 6. So if we want to rotate, it should produce 2, 3, 4, 5, 6, 0, 1. And k is not equal to 2. K is equal to what? 5. By how much we rotate. But where would the guy 0 go? The guy 0 goes to the 5th position. Remember, permutation tells you where you go in terms of going to per Am's point. You were sort of raising the point that you could describe it in terms of where you're going or where you're coming from. Mathematicians always define it in terms of where you're going to. And we shall see mathematicians could make mistakes. Just give me a few more minutes. So that's what it is. While we're doing rotation around M, we're moving everybody by 5 elements to the right. That's what happens. Okay. So it's a little bit confusing, but when you get, you have to sort of, indices are horrible things. You have to always think about it, and you make lots of mistakes. Okay. So prove that we do rotate if we perform distance by its n. This is n, and this is k. The k is the distance from M to L, not the distance from F to M. You're supposed to do it at home, but okay. Once upon a time, there were 2 people, Gries and Mills, very strange couple. And I have to tell you a little bit about them. David Gries is a very important semi-theoretical computer scientist. He is at Cornell. So at Cornell, he is a practitioner, because we will encounter theoretical computer scientists at Cornell later. You have to understand, Cornell, and we have a fellow here, Tom London, who got his PhD from Cornell, was one of the first computer science department in the world. Very, very great. And Gries was one of the original systems guys there, which is a paradoxical thing. I mean, he's clearly not the systems guy, but he was at Cornell. And in many respects, you have to position him in the following sense. He was a popularizer of great work of Edgar Dijkstra, the name which you should know. Dijkstra was one of the 2 greatest computer scientists of my youth. There were 2 great people, Knuth and Dijkstra, Dijkstra and Knuth. And Dijkstra had many wonderful ideas, but he would write them sometimes in somewhat cryptic form. And David Gries would then expose them so that simple people like Cornell graduate students could understand them. There is a very nice book written by him, which I highly recommend, called Science of Programming. It's a popular presentation of the ideas of a very great book called Discipline of Programming by Dijkstra. So discipline of programming is a classics. Science of programming is popularization of this classic. And Gries describes this algorithm in Science of Programming. We'll look at it. So once upon a time, I think it might have been the year 69, he went to Japan. And he went to Japan with another remarkable computer scientist, Mills, who was the chief scientist of IBM Federal System Division. I think that was his official title was. He, in some sense, one of the people who invented something called software engineering, whatever that might be. But he was trying to develop this way how to write good code in large groups and things like that, long, long ago. And these two guys are stuck in some hotel in Japan. And so what do? You know, instead of just drinking beer, they say, let's design an algorithm. Which algorithm? Rotate algorithm. So these two guys from very different parts of computer science designed this fabulous algorithm for rotation, Gries-Mills algorithm. What's the idea? The idea is pretty simple. The idea is like that we have Fm and Ml, and we want to interchange them. Let us, just for the argument's sake, assume that Fm is shorter than Ml. Then we will do the following. We will interchange, do swap ranges till we can. What it will do? It will move the guys from middle to middle plus the length of first to middle into the final destination. But then, of course, the rest is going to be left in unfinished state, because you will have to swap these things to exchange, to rotate these things. So let us look here, okay? And just to make it a little bit confusing, well, no, not for that reason, I introduce some annotation variables. The red stuff you don't need to do the algorithm, but you need to have them to understand the algorithm. So U, we start, U is the length of the first piece, F to M. V is the length of the second piece. Now, if either of these lengths are 0, nothing to do, we're done. Out we go, yes? Now, after that, we do very, very simple thing. We swap ranges F, M, and ML. Okay? So, after we swap, we just say, as long as not both of them are finished, as long as we did not reduce things to 0, what do? We first check, did we exhaust the first range? If we exhausted the first range, then we move middle to first, and our middle becomes where how far into the second range did we get? Otherwise, what happened is that we didn't exhaust the first range. We exhausted the second range. So we just need to reset the first. Because these guys, they are done. And then we do swap ranges, and we go on and go on and go on. What are we doing? Well, let us look at the annotations, guys. Let us not look at the code. So we're saying if u is less than v, then v becomes v minus u. And if v is less than u, then u is equal u minus v. Any reaction? I mean, you spent all this journey sleeping then. This is subtractive GCD. It's not just like subtractive GCD. We're really, these are notations computing GCD. So when we are done, when u and v are equal to each other, what are they going to be equal to? The GCD of the original thing. GCD strikes again. Right? Sort of this is literally subtractive GCD algorithm, which also swaps things as it goes. But the fact that it is subtractive GCD is of great importance, as we shall see, because it will allow us to.
Did they mention that?
Yes, they did. They were good. They didn't quite see all the consequences, but they did observe that it works like subtractive GCD. Yes? So David Gries, at some point he became senile. He wrote a year ago, or 2 years ago, a paper saying that we need to teach programming differently. Before we tell people about iteration and recursion, we should teach them about delegation and inheritance. So when I read that, it became clear to me that the guy lost his marbles, as they say. But sorry, I mean, he did remarkable work. I have very high regard for his book, but programming is about writing while loops, guys. It's not about delegation and inheritance. At least that's my point of view. And it was point of view of Turing, for Neumann, and some other guys who'd never heard of delegation and inheritance, but did know about iteration. By the way, his teacher, Dijkstra, never heard of delegation and inheritance, was able to do work quite well. So however, there is some imperfection here, which forces me to give you a homework. You see, when we do this, we already know which range we hit. So if you inline swap ranges, you could minimize some of these comparisons. You could go directly to where these things happen, right? And that's your homework, to do that. It's not complicated. Right? It's not clear that it makes things faster, because pointer comparisons tend to be sort of so much cheaper than actually doing swaps. And you lose some regularity in the loop structure. So I'm not saying it's going to be faster, but you have to be aware, and one of the things you occasionally need to do is to measure, try to optimize, and see whether optimization helps. So it's a useful thing. So how many operations do we do? Well, every swap which we do puts one element in its final position, except for the last swap ranges, where two elements are put in the last position. So how many swaps do we need? We need, well, I'm going slow. So the number of swaps during the last swap range is GCD, right? And every swap range moves elements along their cycles. Well, I forgot, guys. I apologize. I forgot. I'm just compressing the slides. So this is the one I'm doing. So let me finish talking about that, then go back. So during the called swap ranges, every swap puts one element into the final destination. then during the last swap ranges, every swap puts 2 elements into the final destination. Right? Therefore, the total number of swaps is n minus GCD, nk. And in terms of the assignments, every swap is 3 assignments. And of course, my friend Tom will say, but you could do it with XOR. Doesn't help. It's still 3 assignments. Whether you need a temporary variable or not, it's 3 assignments. You need 3 assignments. So the total number of the assignments is going 3 times n minus GCD nk. Right? Now, we learned another thing, that when we move things, we move them along the cycles. Every swap works among the cycles. So we never change the number of cycles. So what is the number of cycles? The number of cycles is literally how many things in the final swap ranges are left, which is GCD. And why it is important? Because now we know that this algorithm is not optimal. Because it does 3n GCD. And we know that there should be an algorithm. Guys, I'm forgetting. I apologize. Rewind the stack for 3 seconds. I'll come back to it. So this is, by the way, the trace of Gries-Mills. It just shows how it works. And now we go to a very difficult point. You see, in some cases, like in the case of swap ranges, what you return is easy. You see it right away. It's much harder to do it in case of rotate. That is, there is no thing which naturally falls out of Gries-Mills algorithm to return. But eventually, if you use rotate a lot, as I have, you figure out what you would like it to return if you only could. This is this complicated thing that sometimes, and what is this thing? You see, m goes to m prime. M, the middle point, goes to where the first element index with 0, is going to go. Remember, when we were rotating 7 by 2 with 2, the 5th element suddenly became important. Actually, it's the 6th element, but the element with index 5. We index from 0. So it's the thing where the first element with index 0, is going to end. This point, in other words, when I swap these ranges, I want to see where this guy is. It's very useful. We'll see why. And mathematically, it also shows clear because this is the thing which will be the inverse permutation. If you swap, if rotate returns this thing, and you rotate again around this thing, you'll get identity permutation. It's a good point. Unfortunately, Gries-Mills does not allow us easily to return it. So for many years, I had to struggle till I found the correct solution because, again, if you look at the old original STL, it returns void. I knew what is needed, but I didn't know how to do it without doing extra work. It took me quite a while to figure it out. And this is a way I finally figured out how to do it. This is something called rotate unguarded. It is just Gries-Mills algorithm. It's slightly optimized because Gries-Mills, to write it beautifully, I didn't do the following thing. Let me show you some thing which I could have optimized. You see here, I'm saying that if P first equal M, then F is equal m. I could have written p first instead of m because they're equal, yes? And in this clause, I write f is equal to p first. And I do it so that the notation looks pretty. But I actually could have eliminated the else clause and moved this before if. Everybody sees that? Huh? So I didn't do it there for exposition reason, but I do it here. I just put it here, and then it becomes very, very simple. Sort of, I'm just showing that the central loop of Gries-Mills is really very elegant. It's less than 10 lines, so which, remember, is the crucial number. One cannot understand beyond 10 lines. And then it returns the correct result, which is given to it. You see, I give it an extra guy, M1. That's the guy which I need to return. And they just return it. Say, Alex, this is just cheating. Yeah, of course. But therefore, if I have something where I will find M1 but will not complete the GCD, I could call this. That's the devious design. Right? So, and now final version. So it is identical except we do the following thing. We say as long as we can move forward, because what we need to do, we need to find what is M prime. M prime is the guy whose distance to the last is the same as distance of M from the first. Right? It was the guy whose distance from the, remember in our example, the distance of middle from F was 2. And then it moved to the guy whose distance from L backwards was 2. So I organize a loop where I sort of keep going till I find such place. Then I call rotate unguarded and give what I found to this guy to finish up the stuff. Okay, the lesson, you have to actually spend a few minutes thinking about it. It's all right if you don't quite see it. That sometimes you have to think very hard to get the right result without doing extra work. We will see another example of it in 10 minutes after the break.